Hey everyone, ready to unlock some serious brain power.
I like it. Always fun to dive into this stuff.
This time, we're going deep into deep neural networks.
Those intricate algorithms that are like basically changing how machines understand us.
Exactly, especially when we talk.
Like, think voice assistants, real-time translation.
You name it.
It's everywhere.
We've got a stack of research papers here.
Oh, yeah.
Yeah, all about how these deep neural networks, DNNs for short, have shaken up speech recognition.
It's wild how fast it's all happened.
Don't worry, we'll be your guides
Absolutely.
through all the technical stuff
Yeah, we'll make it fun.
so you can impress your friends with your new AI knowledge.
Exactly.
By the end of this deep dive,
Oh, I like that.
you'll be able to explain the magic behind how your phone understands your requests.
I mean, that's what everyone really wants to know, right?
Right.
Like, how does it actually work?
Right, let's set the stage. So imagine you're trying to teach a computer to hear,
Okay, yeah.
like we do.
To hear.
It's not as simple as recording sound waves, is it?
You got it. It's not just about the sound waves themselves.
Right.
It's about teaching the computer what those waves actually mean.
Ooh, interesting.
Yeah, and that, my friend, is where acoustic modeling comes in.
Okay, so it's like translating sound into meaning.
Exactly. Building a bridge between that raw sound and understandable language.
Kind of like deciphering a code.
A very, very good comparison.
So for a long time, the go-to for this was what? The Gaussian Mixture Model,
The one and only.
or GMM.
You got it. GMM.
GMM sounds complicated.
The name's a mouthful, for sure.
Yeah.
But the idea, it's pretty intuitive, actually. Imagine you're trying to, say, recreate a complex shape.
Okay, I like this.
Like a wave, using only a bunch of overlapping circles.
I can picture that, like those things where you connect the dots and it makes a shape.
You got it. That's it. You'd get the general idea, but not all those, like, really fine details.
Okay, so you're saying GMMs worked similarly.
Exactly. They use these combinations of simpler functions
Right.
to represent the sound.
But struggled to capture the nuances, especially as language got more complex.
Precisely. Especially with larger vocabularies, things get really tricky.
So it's like the dial-up internet of speech recognition. Functional,
Uh-huh, I like that.
but pretty limited when you want to download or understand something more.
Right on. GMMs, they laid the groundwork, no doubt, but researchers knew there had to be a better way.
Okay, here we go.
And that's where things get really exciting. Because DNNs arrive.
Because who doesn't love a good tech revolution, right?
I mean, that's what we're here for.
But I'm guessing this shift from GMMs to DNNs wasn't a walk in the park.
Well, you're sensing a theme here.
Uh-oh.
When it comes to AI, there's always a backstory.
Always a backstory. So what's the story? How do we get from those, like, good enough GMMs to the AI powerhouses we hear about constantly?
All right, so picture this. Instead of those overlapping circles trying to, like, approximate a sound wave, imagine a network, like a web, with millions of these interconnected points.
Oh, okay, I'm picturing it.
And each point is a neuron.
Okay.
A tiny calculation unit.
Right.
And they're all working together in these layers to decode the sound.
So it really is deep.
That is the basic idea behind a DNN.
Okay, starting to see the deep in deep neural network. But how do you even start? Like, how do you teach something this complex?
You're asking the million-dollar question. It's one thing to build the network, sure, but how do you train it?
Right.
How do you train it to actually understand the nuance of human speech? I mean, it's tricky.
Yeah, it can't be easy.
Imagine being thrown into a maze with no way out. That's what early DNN training was like.
Oh, wow. Brutal.
Yeah.
So those neurons, those points in the web, need a guide, like a map, to navigate this maze of sound and actually come out with an accurate interpretation.
You got it.
Okay.
That's a really good way to put it, and the breakthrough.
Yeah.
Generative pre-training.
But is that?
So instead of just throwing the DNN into the deep end, we let it play around in the shallows first.
Okay, so instead of immediately trying to decode, like, complex speech, we give it some training wheels first.
I like that. We feed the DNN a ton of speech data, but not to label it, not to translate it, just
Okay.
to find patterns.
Interesting.
Think of it like learning to paint.
Okay, yeah.
You wouldn't sit down and try to paint a masterpiece on your first go.
Right. You need to learn the basics first.
Exactly. You practice lines and shapes, and you get a feel for how colors blend.
So this pre-training is giving those neurons, those little calculation points, a crash course in the basic building blocks of sound.
Precisely. And it's in this pre-training phase that these things called Restricted Boltzmann Machines come in.
Restricted Boltzmann Machines. RBMs, what are those? Some kind of superpowered neuron.
Kinda, yeah. Think of them like mini learning modules within the bigger DNN. They're really, really good at finding these hidden structures in the data. They find those patterns and connections we might not even be aware of.
So, like detectives that can spot clues that others miss, but for sound.
I like that.
That's a good analogy. I'm hooked. Tell me more about how these RBMs work.
They use a technique called contrastive divergence. It's super interesting.
And that's how they train?
Yeah, how they learn to spot those patterns. Imagine the RBM is trying to, I don't know, sketch a picture based on the data it's seeing.
Okay, yeah.
With each attempt, it compares its sketch to the original.
Oh, that's cool.
And it's noticing the differences.
And then it uses those differences to improve.
You got it. Like a game of hot or cold. The RBM fine-tunes its understanding with every comparison until it becomes incredibly accurate at replicating the patterns in the data.
Wow, okay, that's really cool. So we have these RDMs, these pattern-detecting detectives, working hard during pre-training. But then, how do we actually go from that to recognizing words, recognizing sentences? Do we just stack a bunch of RBMs together like building blocks? You're on a roll with these analogies. I'm picturing a whole team of RBM detectives with magnifying glasses ready to solve this case.
That's a great way to think about it. We do, in a sense, stack these RBMs together.
Okay.
Creating what's called a deep belief network, or DBN.
DBN, got it.
It's like assembling a team of specialists, each trained to analyze the sound at these different levels.
Okay, so the DBN is our A team.
Exactly.
But what's the mission? How do we go from pattern recognition to actually understanding what those patterns represent? The words, the sentences.
This is where the real magic happens. So once this DBN is pre-trained, we add on one final layer called the softmax layer.
Softmax layer, another good name.
Catchy, right?
Yep.
Think of it as the team leader who takes all those clues from our detective RBMs and then makes the final call.
I like it.
This layer has a unit for every word or sound that we want to recognize.
So if we're teaching a DNN to, say, understand English, this softmax layer would have a unit for hello, a unit for cat, like that.
Exactly. And with all that information from those pre-trained RBMs, the network can now take in those really complex sound waves and predict what word or sound is being spoken.
Wow.
With impressive accuracy.
It's like all those puzzle pieces just clicking into place.
It is. It's really cool.
But how well does this work in the real world? You know, human language. It's messy. There's accents, slang, background noise. Can DNNs actually handle all that?
That's the question researchers were dying to answer, right?
Yeah.
So they put these DNNs to the test.
Okay.
First on benchmark datasets like
Timid.
Yeah, it's like the training ground for these speech recognition models.
Gotcha. And it crushed it.
DNNs were achieving way lower error rates than anything we'd seen before. They were picking up on these nuances that traditional methods just couldn't grasp.
So it was clear, DNNs, they were the future of speech recognition.
Oh, yeah.
But they didn't just stop at replacing the old methods, did they?
Never. Always innovating.
There's always more.
Exactly.
So what's next?
Well, remember how we talked about GMMs, those earlier models?
Yeah.
Researchers found ways to actually combine the strengths of both.
Oh, interesting. Like a hybrid.
Exactly.
Right.
Creating what we call tandem systems.
A dynamic duo of speech recognition.
I love it.
Tell me more.
So in a tandem system, the DNN, it acts like a high-powered filter, extracting the most important features from that sound data.
Okay.
And then it hands off these like refined features to the GMM.
So it's like the DNN is doing all the like heavy lifting.
Yeah. It's scouting ahead, bringing back the good stuff.
I like it.
And the GMM then can perform way better than it could on its own.
It's incredible. It feels like these DNNs are unlocking this whole new level of understanding when it comes to like us, how we talk.
It really is amazing. And we're just scratching the surface, honestly.
What do you mean? There's more.
Oh, yeah. Way more. One of the big challenges right now is computational efficiency.
What does that mean?
These DNNs, especially the powerful ones, they need a lot of computing power.
Okay.
And that translates to energy consumption.
So it's like this super-powered brain that needs a constant supply of energy drinks to function.
Basically, yeah. That's a great way to put it. And that's a challenge for things like our phones, our smart speakers, all of it.
Right, because we want them to understand us.
Yeah.
But they also need to, like, not drain our batteries in 5 minutes.
Exactly. So it's this balancing act, power versus efficiency.
How are researchers even tackling that?
Well, they're exploring all sorts of really cool stuff, new training methods, more efficient architectures. They're even developing specialized hardware.
Really?
Yeah, it's a really exciting time to be in the field.
So what's like the next big thing? Like, what are you most excited about?
One really interesting area is something called convolutional neural networks, or CNNs.
CNNs, what are those?
So they're actually inspired by how our brains process visual information.
Wait, so we're using insights from how our eyes work to improve how machines understand our voices.
It's wild, right? And it just goes to show how interconnected AI research really is.
That's amazing.
And the applications, they go way beyond acoustic modeling. DNNs are being used to make language modeling better, like predicting the next word in a sentence based on context.
Oh, like autocomplete, but smarter.
Exactly. They're also being used for speaker adaptation, so your phone can actually learn to understand your voice better over time.
That's really cool.
It is, and it's only going to get better.
Wow, so what does this all mean for the average person?
Well, next time you're, say, asking your smart speaker a question, or you're using voice to text.
Yeah.
Remember those DNNs working behind the scenes?
They're learning.
They're constantly learning and evolving.
Wow. It's incredible how far we've come.
It really is. And to think this is just the beginning.
That's always the crazy part. Well, that's about all the time we have for this deep dive.
This was fun, as always.
Always a good time. What an incredible look at the world of deep neural networks and how they're shaping the future of speech recognition.
And who knows what other applications are out there just waiting to be discovered.
Exactly. Always more to explore. Thanks for joining us, everyone. Until next time, keep those imaginations running wild.